Deep inside a 4,500-year-old monument, researchers deployed a tiny, treaded robot. They drove it into a pitch-black tunnel, barely large enough to fit a human arm. The machine crawled through the dark until it came to a dead stop. Blocking its path was a perfectly smooth, sealed stone slab. To understand what traps this little robot, look at the structure surrounding it. This 3D scale comparison illustrates the sheer mass of the Great Pyramid. At 6 million tons, it weighs the equivalent of 12 Burj Khalifa towers stacked together. Even today, engineers equipped with steel cranes and heavy machinery struggle to map out how a Bronze Age civilization moved that much mass. Before we can unseal that hidden door, we have to reverse engineer the raw muscle and mathematics required to build the massive environment protecting it. The pyramid base covers 13 acres. With 6 million tons pressing down on the bedrock, a foundation that is uneven by a few inches guarantees an eventual structural collapse. Today, construction crews rely on lasers to level a site. The ancient builders used a completely different tool. This diagram shows how they carved a grid of long, interconnected trenches across the uneven ground. They poured water into that grid. The water settled to form a flawlessly flat natural horizon line. Workers could see exactly which high spots needed to be shaved down to match the water's surface. With the ground flat, they needed materials. The builders quarried 2.3 million blocks of stone. Some weighed 50 tons, heavier than a commercial semi-truck, and the limestone quarries were located 250 kilometers away. To move them, a human supply chain loaded the blocks onto heavy wooden boats and floated them up the Nile River to the construction site. Lifting 50-ton blocks 480 feet into the air without pulleys required severe logistical planning. This animation illustrates the leading structural theory. A massive network of zigzagging and spiral ramps built up the sides, allowing thousands of men to haul the stones upward on sledges. The construction equipment of the time consisted entirely of human muscle guided by strict geometric rules. Following the robot back inside the dark passageways, the engineering problem changes from scale to precision. The walls of the deepest inner chambers are not made of the softer limestone used on the exterior. They are built from solid granite. Granite is a dense igneous rock. Shaping blocks this smooth requires industrial-grade, diamond-tipped cutting equipment today. The tools we find in the archaeological record look completely inadequate for the job. Workers relied on simple wooden mallets and chisels cast from a brittle mixture of copper and arsenic. The solution was friction. Builders used a flat, toothless copper saw, pouring a steady stream of loose sand and coarse gravel directly into the cut while grinding back and forth against the rock. The abrasive sand did the cutting. Workers dragged these flat blades over the grit for hours, slowly wearing a clean, perfectly straight line through the granite block. That flawless finish was earned through immense patience and months of continuous manual labor, which brings us back to that narrow tunnel, staring down a granite door that was measured, cut, and slid into place exactly 45 centuries ago. Unable to move the stone, researchers equipped the robot with a powerful mechanical drill and bore a tiny hole straight through the rock. They pushed a fiber optic camera through the dust, looking into a hollow void untouched since the pyramid was closed. The camera reveals a silent, dust-covered space. There are no gold treasures or inscriptions on the walls, only the same level, precision-cut stone that lines the rest of the structure. While we still don't know the exact purpose of this room, the effort required to reach it remains the most startling piece of evidence. We sent a 21st century robot into the dark to find a secret. Instead, we found a reminder that the builders achieved this scale and accuracy using only pure grit, the rules of geometry,